Okay, so in this video, we're going to use the definition of the Laplace transform again, but now we're going to find the Laplace transform of a piecewise function. Now, this presents certain issues when we're doing this, and I've seen students make quite a few different kinds of mistakes, and so we want to talk about those as we go. Now, this is the definition of the Laplace transform, and so in order to plug in our piecewise function, it's important to keep in mind that these limits where the function applies have to be incorporated into our integration. So in order to plug this into our definition, the first piece of our function only applies from 0 to 1. So those limits are going to go into our integral. And then the function piece itself goes in as our f of t. It's f of t on this section of the interval. And then e to the negative st dt. And then because of properties of integrals, we're then just going to add on the second piece, which goes from 1 to infinity, because this is from 1 and up. And the piece of the function that we have on this section, f of t, is 2t plus 3. That's f of t, and then we put in our e to the negative st, and we integrate that with respect to t. Now, when we do this integration, the first piece is going to be quite straightforward. It's just e to the negative st. But when we integrate this piece, we're going to have to do integration by parts. And so let's set up the integration by parts for the second piece. So that's going to be u equals 2t plus 3. du is equal to 2 dt, because the derivative of 2t plus 3 is 2. And then dv is our e to the negative st dt. And then v is the antiderivative of that, which is negative 1 over s e to the negative st. Okay, so now if we integrate this first piece, we're just going to basically do this integration again. So we're going to get negative 1 over s e to the negative st, but we're only going to evaluate that piece between 0 and 1. And then we're going to do the other piece. Now the other piece, we're going to do uv for our product rule. So we're going to have 2t plus 3, and then put the constant out front, negative 1 over s e to the negative st from this piece right here, and then minus the integral from 1 to infinity of 2 times negative 1 over s e to the negative st dt. Right? So we can pull the 2 outside, we can pull the 1 over s outside, we can cancel the 2 negative signs. And if we integrate this piece right here, then we're going to end up with just the antiderivative of e to the negative st again, which is 1 over s, as we've seen, e to the negative st. And then these two pieces are going to be evaluated between 1 and infinity. Okay, so what happens when we start plugging things in? Well, when we plug in 1, we're going to get negative 1 over s. And when I plug in 1 for t, I'm going to get e to the negative s. But when I plug in 0, I'm just going to get e to the negative st is 1. And so negative 1 over s without the e. And then we're going to do the same thing over here. We're going to plug in infinity. Well, of course, we have to think of this as a limit. If I plug in infinity into here, I'm going to get infinity times 0, which is an indeterminate form. So think back to L'Hopital's. I put my e to the negative st in the denominator. That makes it e to the positive st, and I get infinity over infinity. I can take my derivatives, and I can quickly see that the exponential is going to go to infinity faster than the polynomial term. And so this whole thing will go to 0 at infinity. But at 1, it's going to go to negative 1 over s times at 1. 2 times 1 plus 3 is 5. E to the negative s, because t is 1. And then I'm going to have negative 2 over s squared. But what happens when e to the negative st gets infinity substituted? What does that do in the limit? Well, that goes to 0 because of the negative exponent. And then minus the minus. And what happens when this goes to 1? Well, e to the negative s. Okay, so now we've plugged in all of our terms. Oops. There we go. So now what can we do? Well, let's see what we can simplify. Well, this thing right here has just got 1 over s. That's 0. I can combine these two terms. This term right here is negative 5 over s, e to the negative s, and minus from over here, minus 1 over s, e to the negative s. And then over here, this is 0, and the only term with s squared in the denominator is minus minus. It's going to be plus 2 over s squared, e to the negative s. And so what I can do is I can combine my e to the negative s terms as 5 minus 1 is 4 over s plus 2 over s squared, and then both of these times e to the negative s. And so this is my Laplace transform for the piecewise function that we started with. Now, one thing to keep in mind about Laplace transforms, they are never piecewise. They are always strings of terms all on the same line. The piecewise portion is accounted for by using the limits of integration. So if you're getting a piecewise function as a result here, it is not correct. Now, very quickly, I want to talk a little bit how to do this from the table. It's going to be based on this idea of a unit step function where everything is 0 and then at 0 it pops up to 1. And so what we can do to use the table is we can rewrite this expression in those terms. So first of all, I'm going to pull out the 1 because I had, if we go back up here, I had 1 and then 2t plus 3. So I'm going to take a 1 out of both terms and pull it outside the function. That's the 1. And so now my first term is 0, and my second term is 2t plus 2, because I pulled the 1 out that goes to both functions. Now, the notation you'll often see for the unit step function depends on the source. Sometimes you'll see u of 1, which is where the jump happens, or u of x minus 1. They're both the same thing. So here, since our jump is happening at 1, I'm going to use this notation to rewrite my expression in terms of t minus 1. Now, if I do that, I have to change the constant here. So I need an expression that these two things are going to be equal. And you can see if you distribute out the 2, you get negative 2 plus 4 gives you the 2. And so now I can replace my t minus 1 with t. Now, this is easy to do for a linear function, but if you get more terms like x squareds and things like that, I suggest using Taylor polynomials to find the expansion in terms of your t minus c. And so what we want to do then is we want to look at our table. So our table for the unit step function says that the unit step function itself is just e to the negative cs over s, which our case c is 1. So that would be just e to the negative s over s. But if we have something more complicated, some function times the step function, then we actually want to be able to take e to the negative s times that function that's being multiplied by the step function. So that's what we were actually doing here. This is a step function, but it's being multiplied by 2t plus 4. Now, if we go down and we look at, if we compare our results, then this 1 out here is just taken from this rule. It's outside the function. And then 2t plus 4, this is our 4, becomes 1 over s, or 4 over s. And then 2t is 2 over s squared, applying this rule. And then times e to the negative 1s, because our shift is 1. Our break happens at 1 and not at 0 or any other function, any other value. And so you can see that the table is consistent with the calculation that we got doing our expression using the definition.